If d of n is a function that gives the number of diagonals of a regular n-gun, determine all fixed points of d of n. First, recall that a fixed point of a function f is a value n for which f of n equals n. Here is an example of the process by which we can compute the number of diagonals in a regular octagon. We may generalize this procedure by noting that we can draw a diagonal from each of the n vertices to each of the other vertices other than the neighboring vertices and itself, yielding n minus 3 vertices, and that in doing so we count each diagonal exactly twice. Setting the formula we derived equal to n, we may solve the resulting quadratic and see that the only positive solution is n is equal to 5. Thus, the only fixed point of d is 5. Let the function a of x represent the area of a triangle with vertices 0, 0, x, 0, and xx. To suppose that a of b is computed for some b greater than 0, and then the function is iterated by computing a of b, a of a of b, etc. Describe all possible behaviors that can occur when the function is iterated infinitely many times. By first noting that a of x is equivalent to x squared over 2, we may observe that the first possible behavior occurs when we have a fixed point of a, which turns out to occur when x is equal to 2. From this we may determine that for x less than 2, a of x is less than x, and for x greater than 2, a of x is greater than x. From this and the fact that a of x is greater than or equal to 0 for all real x, we have these three possible end behaviors.
Consider the following set of transformations. 3 transformations are selected from the set with replacement and applied in consecutive order to the point 0, 0. What is the probability that the final point is also 0, 0? One can approach this problem using casework. The first case to analyze is when the point does not move at all during the transformations. This means that no translations can be used. Because both the reflection and rotation do not affect a point, and there are 3 transformations to apply, the number of possible permutations for this case is 2 cubed, or 8. The second case involves translations. The second case can be divided into 2 smaller subcases as well. The first subcase is when the translations are applied consecutively. The original point can translate right then left, or left then right. The point can also first translate, then reflect or rotate, or be reflected or rotated, then translated. This sums up to 8 total possibilities for this subcase. For the second subcase of the second case, it involves 2 non-consecutive translations. After some reasoning, the second transformation cannot be a rotation, or else a translation would not return the point to 0, 0, and therefore it must be a reflection. There are then 2 possibilities. Both include 2 translations in the same direction with a reflection before applying the second translation. The total number of permutations of transformations is 4 cubed, and tallying up the total 18 possibilities, the probability of ending at the origin is 9/32.